Hey guys, GreatGamer34 here. Today I'm going to be showing you guys something I've been working on and will be released soon enough. So here's the instruction set for it. I'm working on a computer. I'll go more over the instruction set a little later in a Google Drive document where it's easier to see everything mapped out. But basically the purpose of the CPU is going to be so that it can operate with another instance of itself, and share data between the two instances of itself. And it's going to be able to increase what it can do. So how it's going to share that is here's a shared memory bank of 16 bytes. I may make it larger, but right now 16 bytes seems to be perfect. So this is going to act as RAM and as a cache between the cores. So there's that. Over here is the ALU. The ALU was designed by a guy named Embazone. It's got an instant XOR, instant OR, and it's got an instant right shift, which is actually right here. So instant everything on a CLE. So this is a 4-tick CLE adder, ALU, I should say. And it's pipelined right here. Here's the pipeline buffer. So we got a stage on this side and a stage on the other side. This over here, this fancy colored thing, is my instruction decoder. Anything with black means there's going to be no lines coming from it. And don't worry, I'm going to get rid of all the colored wool with a / replace wool with quartz. So I'm going to end up doing that. Here's the ALU opcode decoder, and it tells basically the ALU all the stuff that it can and can't do. And then over here we have our PC. And the PC is actually just another CLE adder designed by the same one designed by Embazone. Except I've made it into a PC right here. And then you'll notice that there's registers underneath the PC. These registers are for holding pointer values. So it's a register specifically meant for the PC called the pointer register. So these lines all coming from here is the branch instruction. So what's cool about the branch instruction is with this bit being toggled, you can either use an immediate as an address, or you can use the first 3 bits of the immediate and use that as a pointer location, depending if the green bit is on or not. So depending on that, it'll flood certain things or unflood certain things here to allow the pointer to work or to allow the immediate to work. And they're talking about pointers in chat right now. How I do my flags actually is I encode the flag as a number between 1 and 4. So there's that. That's 3, 1, 2, and then 4 over here. And then when I pop them out, then I push those numbers into a stack or into a queue to store the flag, and then I can pop the flag and then check it with the flag that I'm trying to check that I want, and if that's true, then I allow the branch to happen. But if it's not true, then I say nope, branch can't happen, don't do it. Somebody also happens to be right here right now, Spitfire, whoever that is. Spitfire LEL, that's the guy. Let's double check. Yep. It's a visitor here. So let's go check out the instruction set. But first, let's bring you underneath the entire CPU. Oh, I didn't show you this. This is the stack. There's a hardware-based stack. There's 8 addresses. I shouldn't really call them addresses, though. There's 8 spots to hold memory. And it comes right off the output of the register. And then it also comes from the output of that back into the bus, the same bus, and then buses up and around and into there. So you'll see that this is like a highway right here for interconnectivity. Yeah, and I've been trying to keep everything synced. 5 ticks there, 5 ticks there, mainly so I can keep this thing as optimized as possible. Alright, so here we are actually looking at the instruction set inside of kind of like Microsoft Excel, but it's Google Drive. So here's everything that can be done. So you'll see 0 is a no op, so it gets nothing. One is add, so it gets register A, register B, saves to register C, and you have an immediate for whatever the fuck value you want it to be. You have that all the way up for logical XOR. And then when you get to right shift, there is no argument B anymore, because there's just no need for it. Instead, you omit that and then write to C. For line 8, it starts getting tricky. Argument A now is your writing register, and you have an 8-bit immediate. So you have these 6 bits plus 2 bits of the red. That makes 8, so you can save an 8-bit immediate into a register if you wanted to. The compare function underneath that, see it right here. So we can compare argument A against argument B, and then by default that pushes that into a flag into a flag stack thing. But it's actually a queue. So here's that right here. Compare with each other, push into a flag stack is actually a queue, whatever. Alright, so now we have our branch. So after you compare, you can then branch. So the branch then pops from the queue, so it'll do the most recent, it'll do the last thing done. And then it has this 3-bit mod. So this 3-bit mod checks for if it's equal to, greater than, if there's a shift underflow, if there's a carry out. And then you have 1 bit that controls whether a pointer or an immediate is used. So that was that green line being used on the CPU that I had. If you saw that, that 1 line toggled between that. And then I can either use an 8-bit immediate, or I can just use argument A, depending if I want to use a pointer or an immediate. It's kind of confusing, but it works very well. My stack instruction takes argument A, and it can either read or write depending on the mod, which is right here. So, for instance, if you want to push into the stack, you have to load from argument A the data that you want to push into the stack. If you want to pop from the stack, you have to then write to a register to save that from what you popped. So then that'll be a write instead of a read, depending on that. Same kind of goes for a pointer instruction, except the pointer, the argument A is these things right here, and this is also part of the pointer stuff. So for a note to myself, the pointer register, when I was building it, I had to remind myself that it's not part of the ALU registers, but it's controlled by the same opcode section. And the argument A is by default, it loads a register and sends it to the PC. When a mod bit, it loads the PC value to a register. So it's just moving data between a register and a PC, which was the whole point of me of having the register underneath my PC. The memory and the cache are now combined into 1 instruction. User interface is moved up, and then I have another instruction underneath here in Minecraft for halt. So basically how this works is, let's get rid of this line. I can't. Okay, anyway, this line and this line are merged together now. So this is controlling that shared memory between the cores. Argument A can either read or write depending on the mod. I can use an immediate, and then here's mod bit. So it can either read or write to cache, respectively. You know, it's as simple as that. And then user interface, it takes a 3-bit address and a write. It's as simple as that. So you can pick where you want to get input from and pull for it, and you can save that input to a register. And that's everything the CPU can do. So I'm back in game now, and here's this the bit that says either this is the bit telling me I either can read or write depending on the mod. So it comes down here, and that's what controls it. If you remember, I was talking about that on my instruction set, that this green line did that. So yeah, this is everything I have so far. I'll keep you guys posted when it's going to be finished, when a map's going to come out, when I'm going to get something programmed for it, when 2 cores are going to be hooked up to each other, that kind of thing, because they'll work fine independently from each other, but when you put them together you get basically twice the performance. You put 4 of them together, you get 4 times the performance. So yeah, that'll be fun, and I'll catch you guys later.